In this video, we'll discuss the process of identifying products of a hydration reaction. Hydration, when most people hear that word, they think of water. During a hydration reaction, water is added to an alkene. This is done in the presence of a catalyst. The catalyst of a hydration reaction is typically a strong acid, so you may see the H plus as shown here, you may see the word acid, or you may see the chemical formula to represent that strong acid. But during the reaction, old bonds break so that new bonds could form. The old bond that is going to break is the double bond of the alkene. And so if we look at this particular compound, we have 2-butene. So 4 carbon atoms with the double bond between carbons 2 and 3. And so when we look at the reaction, the old bond has to break. So in other words, we'll no longer have that double bond between carbons 2 and 3. So we still have carbons 1, 2, 3, and 4. We're not changing the number of carbon. We're only adding to this molecule. What we're adding is water. So for hydration reactions, dehydration, even condensation and hydrolysis, when thinking about water being added or produced during a chemical reaction, it is often easier to think about that water instead of H2H, think about it as HOH, because this represents how it's broken apart and how it's added. Water gets added or removed in the form of a hydrogen and a hydroxyl. So if we think about that, that can help us in predicting the product of the chemical reaction. And so going back to our 2-butene, we've already shown that an old bond is broken. If we go back to the actual structure that was given initially, we have the double bond being located between carbons 2 and 3. And so if we look at those, carbon 2 has a total of 3 bonds around. So that means that it has 1 hydrogen. We know that carbon wants 4 bonds. So it already had 3 bonds, so therefore 1 hydrogen. The same thing with carbon 3. It already has 3 bonds, so therefore it has 1 hydrogen. And so we can look at how these atoms were already arranged, and we still have that 1 hydrogen on each carbon when that double bond breaks. So carbon 2 still has that 1 hydrogen. I will just show it in the same direction initially. Carbon 3 still has that 1 hydrogen. However, carbon 2 and 3 of the alkene, each carbon had 4 bonds. Right now, because I've broken that double bond, right now those carbon atoms only have 3 bonds. So when that old bond broke, it made it possible for the new bond to form. And so again, we have to add water to this molecule. When we're adding that water, one side gets the H, the other side will end up getting OH. And so in order to determine which one goes where, we can look at how those atoms are arranged around the carbon atoms where the double bond was originally located. So you actually have 2 different options, because we can see it where we have that second hydrogen's already had 1 hydrogen, but I can say that my second hydrogen also goes to that carbon. I have 1 hydrogen on carbon 3. I can show this hydroxyl here, which of course will end up changing the number, so it's no longer carbon 3. Looking at this, this gives me the structure of 2-butanol. I could have done it the opposite way. So I could have showed that the OH went to that carbon. It already had a hydrogen there, so we still have that 1 hydrogen. This carbon already had a hydrogen, but now if the OH went to that carbon, that means that the hydrogen will go to this carbon. If we look at this compound, again, we have 2-butanol. So for this particular hydration reaction, we ended up with a symmetric molecule. In other words, it was the same forwards as it was backwards. So if we go from left to right, we have trans 2-butene. If we go from right to left, we have trans 2-butene. So that molecule was identical forwards and backwards. So as a result, it didn't matter which carbon actually gained the hydrogen and which gained the hydroxyl, as long as they each gained a new bond. For this particular reaction, they would both result in the formation of 2-butanol. But of course, that's not always the case. So let's say we had this compound still performing the hydration reaction. So now we're looking at 2-methyl 2-butene. So again, during this process, we can look at our hydrogen atoms. So where carbon 2 is located, it already has a total of 4 bonds. So that carbon won't have any hydrogen. It already has 4 bonds. The next carbon, carbon 3, has 3 bonds that are shown. So therefore that indicates that this carbon has 1 hydrogen. So if we look at the possible products of this reaction, so we can show where the double bond has been broken. I'll just show them here. So we no longer have that double bond. Still have the methyl. Still have the hydrogen. I'm going to draw this methyl at an angle. And so I have to add my water. Again, we're adding HOH. So I can add the H here, meaning that I would add my OH here. Or I could have did the exact opposite. I'm going to make them side by side this time. Still have my methyl, so I can't change where my methyl was located. I can't rearrange the atoms. But now I can say, okay, well maybe my OH went to this carbon. If my OH went to that carbon, that will indicate that the hydrogen had to go to this carbon, and we already had this hydrogen. So we have 2 possible products. So here I'm showing the actual hydrogen, but of course you don't necessarily have to show those. So essentially what we have is this compound versus this compound. They both have the same type and number of atoms, but they represent different compounds. The structure to the left. So that alcohol represents 2-methyl 2-butanol. So 2-methyl, because the methyl is on carbon 2. The alcohol functional group is on carbon 2. We have a total of 4 carbon atoms. Here, now we have 3-methyl 2-butanol. Because remember, we can number our parent chain from left to right or right to left. But you want to number so that your functional group gets the lowest number possible. So here we went left to right. But here we're going right to left. Oops. Even though it causes my substituent to have a higher number, it gives my functional group the lower number. So you see we have 2 different types of alcohols that are formed. 2-methyl 2-butanol, 3-methyl 2-butanol. Both alcohols, but different types of alcohols. The alcohol to the left, if we look at that alcoholic carbon, so the carbon that the OH group is attached to, it's attached to a total of 3 carbon atoms. So here we have a primary alcohol. If we look at the structure to the right, that alcoholic carbon is bonded to 2 carbon atoms. So here we have a secondary alcohol. If you were to perform the hydration of 2-methyl 2-butene in a laboratory, you would see a mixture of both products, but you would see more of one than the other. The product that you would see more of is called the major product. The product that you would see less of is your minor product. This tertiary alcohol will give you your major product. The secondary alcohol will give you the minor product. The way you determine which alcohol represents your minor product is by utilizing Markovnikov's rule. Markovnikov's rule tells us that in this hydration reaction, when we added the hydrogen and we added the hydroxyl, the hydrogen of the major product, well, in order to determine the major product, the hydrogen goes to the carbon of your alkene, so your original reactant. It goes to the carbon that had more hydrogen atoms. So going back to our original alkene, in that original compound, we had our double bond. So we're looking at those two carbon atoms, carbons 2 and 3. Carbon 2 didn't have any hydrogen. It had 0. Carbon 3 had 1 hydrogen. So Markovnikov's rule tells us that the hydrogen of water will go to carbon 3 because it had more hydrogen. So therefore the hydroxyl will go to carbon 2. So in order to determine your major product, think about Markovnikov's rule. Look at how many hydrogen atoms are around the carbons where your double bond is located. Whichever had more hydrogen would gain the hydrogen of the water. Whichever had a fewer number of hydrogen or had more carbon, you can look at it either way, that is where your hydroxyl will go. And so our major product was that tertiary alcohol. What you will see when utilizing Markovnikov's rule, if you have an option between a tertiary alcohol and a secondary alcohol, or even a primary alcohol, the more substituted alcohol is going to be your major product. By substituted, it's simply referring to how many carbon groups are bonded to that alcoholic carbon. So in other words, the tertiary alcohol is your favorite product. If you can form it, it'll form. Secondary alcohol is favored over primary alcohols. And so this allows us to predict the product of a hydration reaction. Of course, this is the general rule, but there are exceptions. So let's look at one exception. The exception will typically come up when dealing with biochemical reactions. And so chemical reactions that involve biomolecules or compounds that are important for biological function. So in some cases you may encounter compounds that have a double bond, so an alkene, but they may also have a carbonyl group. When doing the hydration of this type of compound, so if there is a ketone or a carbonyl group 2 carbons away or next to one of the carbon atoms of your double bond, so depending on which carbon you're looking at, so look at either end of that double bond. If it's a carbon of a carbonyl right next to it, so this carbonyl is right next to it. In that case, that will help determine where the hydroxyl goes. So if you have these 2 functional groups right next to one another, the carbonyl group, so in this case our ketone, as well as the alkene, that dictates how the hydrogen and the hydroxyl are added to this compound. So instead of utilizing Markovnikov's rule, you'll still go through the process of breaking the double bond. So we still have this carbonyl group, but we don't have that double bond. Instead, now the alcohol, so the hydroxyl group, is added 2 carbon atoms away from the carbonyl group. So whichever carbon of the double bond was 2 carbon atoms away, that is the carbon that will gain the hydroxyl, so that OH. So you have your carbonyl, your carbon-oxygen double bond, 2 carbon atoms away. So remember, these were the 2 carbon atoms where your double bond was initially located. So this carbon is 1 carbon away. This carbon is 2 carbon atoms away. This would be the carbon that would gain the OH. So even though you may see a very small amount of the opposite carbon with the OH, this is going to give you your major product. So this is an exception to the rule when looking at hydration products. If there is a carbonyl group present and that alkene is right next to it, when that hydration reaction takes place, the hydroxyl moves to the carbon that is 2 carbon atoms away from the carbon of the carbonyl. If you don't have that carbonyl and that alkene present, then you simply apply Markovnikov's rule. Again, his rule tells us that the hydrogen goes to the carbon of the alkene where your double bond was located that had more hydrogen. The hydroxyl will go to the opposite carbon.